nuclear physics lecture. I'm Dr. Parvez Ahmed, and this lecture we will talk about classifications of neutrons reactions. So let's start our lecture with classification of neutrons reactions. So you know that whenever neutron interact with the matters, so the interactions with the matters of the neutrons might be with respect to a few parameters with respect to that parameters. It can be different kinds of the interactions. The interactions of the neutrons with the matters can be elastic scatterings or it can be diffractions, elastic or diffractions. It can be inelastic scattering. Uh, it can be absorptions, neutron capture, and it can be neutron induced fission. So I mean, these are the major kind of the neutrons reactions, and this is the some of the classifications of major interactions of the neutrons with the matters. That is, whenever we have neutrons, and remember, whenever that neutrons, we fire it on a target, just like you can see it here. An example of the bullets that interact with the target. So what actually happens, that is the possibility is that either the bullet might be scattered, it might be goes to make a hole inside the target, or it may splat the target, or it may be recalled back, or it may be scattered by the target, just like you can see it here. So the same by similar way, neutrons can have interaction with the matter. So the interactions of the neutrons with the matter is being classified in these following types. That is, it can be elastic scatterings or diffractions. It can be inelastic scattering. It can be absorptions. That is neutron captures. It can result in neutron induced fusions. So let's talk about the nuclear reactions. That is fast neutrons interactions. Fast neutrons basically when they interact with the matters. So mostly in the case of elastic scatterings, neutrons interact with the particles of the approximately the same mass, such as protons. So the example of such a kind of interaction is like a ballet ball analogy. I mean, it's the elastic scatterings of the neutrons when it interacts with the particles of approximately the same size, just like that of protons. It's exactly the same, just like that of ballot ball. I mean, when the particle size, with which you want the neutrons to collide, and as a result, we were saying that collisions that should be elastic collision or elastic scattering. So the necessary or the important fact for that kind of reaction is that the particles size should be the same as that of the incident neutron. So in that particular case, we will have elastic scattering. So this kind of scatterings occurs in materials rich in hydrogens, such as waters, wax, and concrete. That is, elastic scatterings of fast neutrons. It occurs from a kind of materials in which we have hydrogens and majority. The example of such a materials are waters, wax, and concrete. Similarly, it's account for about 80% of fast neutron dose to tissues. I mean, this was the example. I mean, these are the example of elastic scattering of the neutrons. I mean, it's a type of the materials in which the elastic scattering occurs for the fast neutrons. And here we saying that it's occur mostly for the materials which is rich in hydrogens. And we're saying that for the fast neutrons dose, I mean, it's account for about 80% of fast neutron dose to tissues. So inelastic scattering, in a case of inelastic scatterings, neutrons interact with the particles of much greater mass the example of which is irons. If we take the example, just like we took the example of ballet ball for elastic collision, so here for inelastic collisions, we can take the analogy or the example that of table tennis ball versus a bowling ball analogy. So what it means? Let me explain again. Uh, I mean how the neutrons are fast neutrons. I mean we have an inelastic scattering. So fast neutrons interact with the particles of much greater mass. For example, iron. I mean, irons is an element which has a greater mass. When fast neutrons interact with these greater mass particles, so in that particular case, inelastic scattering occurs. And the analogy for this kind of reaction is that of a tennis ball versus the bowling ball. I mean, you people know what's the size of the tennis ball and what's the size of the bowling ball. So as a result of these interactions, we have inelastic scattering. So what happened in inelastic scatterings? So in inelastic scatterings, you know that it's well known for the physicists that in inelastic scattering, the kinetic energy and momentum are not conserved. I mean, this is the well-known fact. All the people, all the physicists that they are well aware of this fact. So what actually happened? Some of the kinetic energy is transferred to the target nucleus, which excites the nucleus. The excitation energy is then emitted as a gamma rays, photons. So that's what's happening in elastic scatterings. So furthermore, in inelastic scatterings occurs primarily with the high atomic observer. I mean, with the high atomic numbers element or observer. So just like we here mentions that we took the example of iron. So in this particular point, we are explaining the same fact. So what is that? Is that inelastic scattering occurs primarily with the high atomic number observers. That is, it's mostly occur with those atomic number. I mean, with a high atomic number observer. You know that last time in previous lecture we mentioned about different neutron observer. So inelastic scattering is basically possible. I mean, it's for high atomic number observer. I mean, we have neutron observer, and those neutron observer we have some which has high atomic number. So this kind of scattering mostly occur with the high atomic number elements. So for fast neutrons of energies of about 1 mega electron volt, inelastic scattering can become appreciable. This fact should be noted that for fast neutrons of energy of about 1 mega electron volt, inelastic scatterings can become appreciable. Uh, if we take the example of the human tissue, just like we mentioned on the previous slide for elastic scattering, uh, so here in the case of inelastic scatterings, if we consider the example of the human tissue, so for the fast neutron energies in excess of 10 mega electron volt, inelastic scatterings and nuclear reactions frequently with emissions of several particles become comparable in frequency with the elastic scattering. So this is an human tissue. I mean, what happens if you have fast neutrons and you are saying that those fast neutrons they are responsible for inelastic scattering. So if we consider this elastic scattering of fast neutrons in human tissues, so in human tissue and for the fast neutron energy in excess of 10 mega electron volt, inelastic scattering and the nuclear reactions becomes comparable in frequency with elastic scattering. So this is something very much remarkable. So for elastic scatterings, I mean, if you're persons, I mean, you are new in the field of physics, and you want to know about the elastic scattering of the neutron, so you should consider this diagram. That is, before the collision, we have a situation like this. We have a particle at rest, the target particle at rest. We bombard or we strike, it's a projectile uh, which has initially some velocity, and we fire that at the target. So when we strike it or we hit it, there is this target. So after that, the projectile and target, they both move with the same velocity. After the collisions, they both move with the same velocity or same kinetic energy until unless it scatters in different direction. Even if it's scattering different direction, so even then that the momentums and energy is being conserved. So this is an example of elastic scattering. This is how the neutrons, elastic scattering of the neutrons occur. It's a general examples for general understanding, but elastic scattering of neutrons occur by the same analogy. Similarly, if we consider inelastic scattering of the neutron, so we can have the journal example for inelastic scattering, which can be like this. We have the target, and that target we bombard a neutron. Before collision, we have situation like this. We have neutron that's moving with certain velocity toward the target. So for some moment, we say that momentarily both the masses are united. This is situations like you can see it here. uh, in this particular case, until it's reached this particular state, so we say that momentarily both the masses are united. So after the collisions, when the collisions happen, so after the collisions, excess energy is emitted as electromagnetic radiations, that is in the form of gamma rays photon. So that's why we're saying that some of the kinetic energy that's being lost. So this is the example of inelastic scatterings. It's for the neutron. The neutron inelastic scattering occur by this same analogy. So charged particles emissions are neutron charged particle emission reactions shown by neutrons capture and boron, which you can observe here. It's an example of charged particle emissions, or we say that neutron and charged particle emission reactions. We have boron 10, and that boron 10 is when hit by the neutron. So as a result, we get two charged particles, that is lithium 7s and alpha particles. Along with that, we have some energy that we call the Q values. Similarly, we can have radioactive captures or neutron gamma reactions shown by neutron capture and stable cobalt. That is, we can write it like this: neutron gamma reactions. As example, we can have neutrons. We can have cobalt 59s, and we say that cobalt 59 is when hit by the neutron. So as a result, that cobalt 59 is converted into cobalt 60, and that cobalt 60, it's captured the neutron. It goes to excited state, and then it de-excited by the emissions up to gamma rays photons. We can also have fission reactions. In a case of fissions, the product that we can see it here, we fire neutrons in uranium-235 nucleus. So the fission product here, first the target nucleus, which is uranium-235, it goes to excited state and make an excited nucleus, that is uranium-236, and this is highly unstable uranium isotope. Then it goes to a fission. So as a result of fission, we get a molybdenum 95 and lanthanum 139. It correlates with the fission yield probability. So 95 and 139 add up to only 234, not 236. Since generally two or more neutrons, that is if we take an average, so an average 2.5 of neutron is emitted from each fission event. So this is a kind of a good example of fissions, in which we have at the average 2 neutrons, 2.5 neutron. Uh, So as an example of the neutron absorptions and the production of the charged particles that we mentioned on the previous slide for the boron 10s, you can see it, you can observe it here, this particular diagram, this particular photograph. So here you can see it. We have boron 10s. This is the boron 10s in green colors. And blue we have the neutrons. So when we had this boron 10 with the neutrons, so after that the boron 10 is converted for a certain moment of time, is converted into boron 11s. So after that it's being disintegrated into two particles, two daughter nuclei, that is lithium 7s and alpha particles, along with the gamma rays, that is in the form of the energy. So this is an example of a neutron observer and charged particles reaction, just like you can see it here in the form of reactions. So here you can see it again. So initially, as you can see it here, when the reactions occur, so as a result of that reactions, we have lithium 7 in excited state. That's why we say this in reaction in excited state with alpha particles, and this is being de-excited. This lithium being de-excited by the emission of soft gamma rays with the energy of 480 kilo electron volt. Similarly, as a neutron reactions, we can have the example of breeding plutonium 239s from uranium 238s. It's an example of neutron capture. So here you can observe we have a neutrons, and with that neutrons, it strike a non-fissile atom of uranium 238. It's a breeding example of breeding plutonium 239. So we strike a non-fissile atom of uranium 239 with a neutrons. So what happens as a result of this striking, we have two beta particles are given up. So what happened is these as a result of these two beta particles, we have the results and the form of fissile plutonium atoms. So this is how we can get the breeding of plutonium 239 from uranium 238. That is a fissile plutonium atoms from non-fissile uranium 238 atoms. So here you can see the example in the form of reactions. That is, we get uranium 239s, which has life or half-life equal to 23.5 minutes after it goes to beta decay. So as a result of beta decay, we get neptunium 239s, which has a half-life equal to 2.3 days, which again goes to beta decays, undergoes beta decay. As a result, we get plutoniums 239. Nuclear reactions, that is with a charge particle bombardment. So as a result, we can have just like for example, we can have zinc 68, and when we bombard that zinc with a proton, so as a result, we get gallium 67 plus 2 neutrons. So this is an example of nuclear reactions of charged particles bombardment. That is, we bombard charged particles on a zinc nucleus. So as a result, we can also get the neutrons. Another example is that of the charged particle bombardment is we strike alpha particle with oxygen 16. So as a result, we get fluorine 18 plus proton and plus neutron.